Chapter 23 in this course talks about the reactances, the AC circuit with resistances and reactances. So we're going to look at the AC circuit with resistances alone, and then with the inductive reactances alone, with the capacitive reactances alone, and then look at the reactions of the two opposite reactances, that they cancel each other out. And then we look at the series reactances and resistances, and then we look at the parallel reactances and resistance circuit, and at toward the end of this section we talk about the series parallel reactance and resistance. And then real power AC meters, watt meter summary of types of ohms in AC circuit and the phasors in the AC circuit would be another lecture video. Here, if we have only resistive circuit, there is no reactive part. Therefore, there is no lead or lag in the current and voltage relationship with each other. So in the series circuit, as you know, the voltages add up to be the supply voltage, and in the parallel circuit, the branch currents add up to be the total current. Suppose we have only a circuit reactive with only inductance in the circuit. In that case, well, you know, for the inductance, the voltage leads the current. So if you look at the two inductances in this case, they each are 50 ohms, so they will be in series with each other, and they are additives. So they add up to be 100 volts, which is applied from the source. And of course, there's a phasor relationship here between the capacitive, between the inductive current and voltage waveform, which is 90 degrees. And a way to not to confuse the relationship between the voltages and currents in inductors and in capacitors, we can actually look at this note over here, like Eli the Iceman, for L being the inductor and E represent the voltage and I the current. So in the inductor, the voltage leads the current, whereas for the capacitor C, the current leads the voltage E. So if you remember Eli the Iceman, and then you can figure out the relationship between the inductor, the current, and voltages, and so the capacitive voltage and current as well. And so if you have the two inductors in parallel, then of course the two inductive current, which are at 90 degrees with the voltage applied, they are additive in this case. Again, there is 90 degrees of phase shift between voltages and current waveform. This is another circuit with only the capacitive part. Now in the capacitive part, the things are reversed. The current leads the voltage by 90 degrees, and the voltage lags the current by 90 degrees. Then again, if we look at this again, denote the Eli the Iceman for the capacitor here, the current is going to lead the voltage. So the current, which is on the horizontal axis, and the voltage is on the negative vertical axis, because the voltage is now lagging the current. Therefore, if we have two capacitive circuit, so we have capacitive reactances. In this case, there is no resistance in the circuit; they're just pure reactives. Then the currents are again additives. So therefore, the combination of the capacitor and resistor and inductor and resistor, they have opposite phasors. When analyzing the series circuit, opposite reactances in the series must be subtracted. So the capacitive and the reactive inductive reactances are have to be subtracted in the series circuit. Of course, if the reactive of the inductive reactive is larger, the net reactive is inductive. If the capacitive inductive is larger, of course the net reactive is capacitive. So here the important notes here is that in a circuit that has both the X of L and X of C, The opposite phase angles enable one to offset the effect of the other. So for X of L and X of C in series, the net reactance is the difference between the two series reactances. In parallel circuit, however, the net reactive current is the difference between the IL and IC, the branch currents. In another word, pictorially put it together, if you have a series circuit with the inductor and a capacitor with no resistor in the circuit, then of course the reactives of the two are in opposite direction to each other. So the 60 and 40 are subtracted, and the net reactive part in this circuit is only 20 ohm, which gives us a 6 amps of current going through it. So if you notice, the reactances are 180 degrees out of phase with each other, so they actually negate each other's effect. If you have the capacitor and the inductor in a parallel circuit with your AC voltage source, in that case the currents are in different directions, in the opposite directions. So the current to the capacitor and inductor are 180 degrees with each other, and we have a net current between the two of 1 amp only. So another important points here when you're doing the analysis on the resistive reactance of the circuit, the effect of the series reactance and resistances must be combined in a phasor diagram. For circuits, series circuits, all the ohms of the opposition are added to find the total impedance, Z of t. First, add all series resistances into one total R. Then combine all series reactances, adding all XLs and all XCs and finding X by subtraction. Then the total R and X net can be added by phasor computation to find the total ohms of the opposition in the entire circuit. Putting it in equations is that after the total R and net reactances are found, they can be combined into the right angle triangle equation, which is the hypotenuse of the right angle triangle equal to the square of the sum of the square of the sides. The same thing for the parallel circuit, and the total current is equal to the phasor addition of the resistive current and the inductive current, or reactive current rather. Parallel IC and IL phasor are also opposite with each other. You can see opposite current in parallel branches are subtracted, and if the total current is inductive, the circuit is inductive. If the IC is larger, then of course the circuit is capacitive. So if we analyze this little parallel circuit here, which consists of a AC source of 120 volts, we have the capacitive reactance of 60 ohm, and we have the inductive reactance of 24 ohms. So here we can figure out each current in each branch because they have 120 volts applied across all parallel components. So 120 volts divided by 30 ohms gives me 4 amps. For the resistive current, divide that voltage by 60 ohms gives us the current through the capacitor, and of course the current through the inductor is found out by dividing 120 volts by 24 ohms, which gives us 5 amps. So the net current, inductive net current, is 5 minus 2, which gives us 3 amps here, and that 3 amps is squared and added to 4 amps squared, which is the current through the resistor, and get the square root to get a total current of 5 amps. The diagram below shows us the current in the circuit. The net current here is inductive, as you can see in blue, and it's pointing downward, so the current is lagging. And of course the 4 amp is the resistor, which is on the horizontal axis, so the total current is at 5 amps, which is the diagonal of the triangle. And then you can go ahead and figure out, for example, what is the equivalent impedance of a circuit by dividing the voltage by the total current in this case. So it becomes 24 ohm. And you can even find out what is the phase angle here, what is the lag angle here in this case, because it's mostly inductive, so the current is going to lag the voltage. So if you do the equation, it is the reactive part, the net reactive part, divided by the net resistor current. So the ratio of the two currents gives us the tangent, and we get the inverse tangent, of course, with the negative angle, because we know it is a more of the inductive reactance. Now, of course, if you have the series parallel reactances and resistances in the circuit, you can just treat them like a regular series parallel resistive circuit. For example, if you look at figure A here, you start up with the two R1 and R2, which are in parallel with each other, 200 ohms. So we can replace this with one resistor of 100 ohm, and then we have a reactance in a branch of an inductive reactance of 600 ohm, a capacitive reactance of 400 ohm. Those two would cancel each other, so the net real result is 200 ohm inductive reactance. And the third branch has only two inductive reactances which are in series, and they add up to be 200 ohms. So this becomes one little circuit, and then we can analyze this as a series circuit, and we find out what the total impedance is by using the right angle triangle formula, which comes out to be 141 ohms. So here are the waveforms and phasors for the series RCL circuit. If you look at this, for a series circuit, of course, you know there's only one current in the circuit. So they're showing here the relationship between the current and the voltages. The current are in blue, the voltages is in red. For the resistor, there is no phase difference, as you can see on the top. They are all in phase with each other, but the waveform across the capacitors, if you look here, okay, is the current is leading the voltage is lagging. And if you look at the for the inductor, the voltage is leading, whereas the current, which is in blue, is lagging. So they're showing the relationship here with the relationship between the current and voltage in the capacitor and the current and voltage in the inductor. Again, the formula or the saying is Eli the Iceman. If you remember that, you can figure out the relationship between the capacitor and inductor in that form. So if you have a series circuit, well, of course, in this case, like we said, it's only one current, and then in this case, again, you have the two reactances that are opposite to each other, so you get the net reactance of 12 minus 9, which is 3 ohms. So that 3 ohms is going to be underneath that square root equation with 4 ohm, which is the resistive part, and then gives us a 5 ohm of the impedance. So once we have the impedance, we know the applied voltage is 20 volts. We divide the two, you get 4 amps for the current. Of course, if you look at the two reactances, you can see the capacitive reactances is more, so the circuit is basically capacitive. So here is the net result. As you can see, the net result is the 3 ohms in the down position, 4 ohm, which is the resistance, and then you get the 5 ohm, which is going again, you have the angle here, which is going to be negative again. If you do this further, the tangent of the angle, again, it is the net reactive part over the net resistive part. So the net reactive part was 3 and 4 ohm for the resistive part, so you get the inverse tangent with the negative sign, gives us minus 37 degrees. So since the circuit is capacitive, the source voltage, in this case, lags the source current by 37 degrees. So let's look at this circuit. We have 20 volts, again with the 12 ohms and 9 ohms. So if you do the calculations, you subtract the two, we get 3 ohms for the difference between the reactive parts, and then said the total impedance is 5 ohm and current is 4 amps. So once we have the current, we multiply the current by the reactances and the resistances to get the voltage drops here. So you can see the voltage drop across the capacitor is 48 volts. The voltage across the inductor is 36 volts. So to get the total voltage applied, which should be 20 volts, we have to subtract VL from VC to get 12 volts, and then square that one plus the square of the 16 volts, and then get the square root to get 20 volts, the total voltage applied. Okay, let's take a break.